Gregor Mendel was far more than a monk in a garden. He was a rigorous data scientist before the field existed. By applying the systematic observation of a meteorologist to the biological world, he transformed peasant intuition into the mathematical bedrock of heredity. This visual represents the moment biology became a predictive science. Notice the transition from sepia history to the neon complexity of the double helix. It illustrates how Mendel's ratios like 3:1 and 9:3 to 3:1 provided the foundational logic for the genomic revolution, ultimately empowering us to decode life itself. We often dismiss Mendel as a lucky hobbyist, but this slide shatters that lonely monk myth. Look past the habit and you'll find a master of experimental design. Mendel didn't just grow peas, he engineered a data stream using the binomial distribution to ensure mathematical certainty. By achieving a p=0.001 level of significance, he wasn't guessing. He was proving the laws of inheritance with precision that modern labs still emulate. His true legacy isn't gardening, it is the birth of quantitative biology. This rigorous approach is what allowed him to see patterns where others only saw plants, turning a quiet monastery into the epicenter of a scientific revolution. To understand Mendel's genius, we must deconstruct the caricature. The reality is far more impressive. Mendel was a university-trained physicist and mathematician whose mastery of combinatorial logic allowed him to see what others missed. He wasn't working in a vacuum. He was a networked scientist, corresponding with Europe's elite and publishing pioneering research on meteorology. By integrating these many sides, from tornado tracking to award-winning breeding, he applied a cross-disciplinary rigor that birthed modern genetics. This slide proves that his discovery wasn't a gardening accident, but the inevitable outcome of a brilliant, highly connected mind applying hard science to the natural world. Mendel's path to science was forged in trauma, not leisure. This timeline reveals the high stakes of his burden of genius. When family tragedy ruined their livelihood, the resulting pressure pushed Mendel to a psychological breaking point. His career, and the future of genetics, was only saved by his sister Teresa's selfless sacrifice, trading her own future to fund his education. By entering the Abbey of St. Thomas, Mendel wasn't retreating from the world. He was securing the stability required to think. This sanctuary transformed a struggling peasant into the revolutionary scientist, who would eventually unlock the code of life. Mendel's genius needed more than a garden. It required an institution. The Abbey of St. Thomas was a premier research facility, providing the specialized infrastructure for his 30,000 plant experiments. From the precise data of the meteorological station to the cutting-edge library, Mendel was immersed in a state-of-the-art scientific environment. Most importantly, Abbot Cyril Knapp acted as a shield, protecting Mendel's profane inquiries from conservative interference. This sanctuary wasn't just a home. It was a deliberate incubator for the future of genetics, providing the resources, the data, and the political cover necessary to redefine biology. Mendel's genius was forged at the University of Vienna, where he mastered a synthesis funnel of disparate disciplines. Under Christian Doppler, he learned to seek absolute physical laws through experimental rigor. Andreas von Eddingshausen equipped him with the tools of combinatorial math and probability. Finally, Franz Unger introduced him to the then radical concepts of species change. By funneling these three worlds into a single prism, Mendel created an entirely new, quantitative approach to biology. This wasn't just observation, it was the application of hard physics and statistics to the mystery of inheritance, providing the definitive, predictive framework that modern genetics relies on today. Mendel's greatest asset wasn't his garden, it was his obsession with data. For 3 decades, he acted as a pioneer in European meteorology, tracking daily climate patterns with relentless precision. Whether documenting violent thunderstorms or mapping the path of a tornado, Mendel was hunting for hidden natural laws within massive datasets. This slide reveals the core insight. His discovery of genetic ratios wasn't a stroke of luck, but the inevitable result of applying 3 decades of rigorous, statistical weather tracking to the biological world. He didn't just study peas. He engineered a new way to see the laws of life through the lens of long-term data. Mendel's peas were actually a proxy for sheep. At the time, Brno was a global textile powerhouse, but breeders were facing a costly mystery. Why did valuable traits in their livestock suddenly vanish or reappear? This wasn't just a scientific curiosity, it was an economic emergency. Mendel stepped in as a community problem solver, leveraging his botanical skills to answer a question born directly from the pastures of Brno. By applying his rigorous methodology to plants, he provided the predictive logic that breeders desperately needed. His discovery wasn't just a win for biology, it was a strategic solution designed to power the agricultural engine of his home. Mendel's great leap was moving biology from analog to digital. In Darwin's era, Scientists believed inheritance was like mixing paint. Once blended, the original colors were lost forever. This blending theory made evolution nearly impossible to track. Mendel shattered this by proving that traits are particulate. Like marbles in a jar, genes can be stored together without ever losing their individual identity. They are discrete, untouchable, and capable of being separated again in the next generation. This fundamental shift allowed us to understand how variation persists, providing the essential mechanism that Darwin's theory lacked. It changed our view of life from a murky soup to a precise, predictable code. Mendel didn't just discover the laws of inheritance, he engineered them through a feat of endurance. This was a three-phase operational masterpiece. First, he spent 2 years ensuring his starting data was clean through true breeding. Next, he isolated exactly 7 binary traits to eliminate complexity. Finally, he scaled, manually crossing 300,000 Ps over 9 exhaustive years. This massive sample size provided the statistical power necessary to reveal the 3-to-1 and 1-to-2-to-1 ratios with undeniable certainty. By combining this sheer scale with mathematical rigor, Mendel forced the hidden laws of biology to finally reveal themselves, setting a new gold standard for scientific inquiry that remains the backbone of modern research. Mendel's 3-to-1 ratio is the smoking gun that proved inheritance is a digital code. By crossing pure yellow and green peas, he observed a total disappearance of the green trait in the first generation, the law of dominance. However, the true breakthrough occurred in the second generation, where the green trait returned with mathematical precision. This proved the law of segregation. Traits don't blend or dilute, they remain discrete, immortal elements that can hide for generations before re-emerging. This discovery provides the ultimate benefit to evolution. It ensures that rare, potentially vital variations are never lost to the soup of the majority, keeping the library of life diverse and adaptable. Scientific progress often hinges on the right connection at the right time. This slide captures the greatest missed opportunity in biological history. While Darwin revolutionized our understanding of evolution, his theory was haunted by a missing mechanism. He couldn't explain how traits persisted without diluting. Ironically, the answer sat on his shelf. Mendel had already unlocked the digital code of particulate inheritance through statistical experimentation. Had these two worlds collided, the modern synthesis would have begun decades earlier. Darwin possessed the vision of life's journey, but Mendel held the engine's blueprints. Their separation reminds us that even the most brilliant discoveries require a bridge to change the world. Mendel's failure to achieve immediate fame was actually a testament to his advanced thinking. This slide illustrates a profound intellectual mismatch. While 19th century biology was purely descriptive, Mendel was operating in the realm of predictive statistics. He was a man out of time, bridging two worlds that had no common vocabulary in 1865. The benefit of this perspective is clear. It reminds us that true breakthroughs often occur at the intersection of unrelated fields. Mendel's isolation wasn't a sign of insignificance, it was the price of being a pioneer. He provided a mathematical foundation for life before biology was ready to count, proving that the most transformative ideas often require the world to catch up to the genius. Mendel's silence was eventually shattered by an exponential explosion of discovery. Once biology caught up to his mathematics in 1900, the world gained an unprecedented power over the code of life. This timeline shows the direct evolution from pea-plant ratios to the chemical reality of DNA and the mapping of the human genome. By proving that life is governed by a precise, predictable logic, Mendel provided the foundational blueprint for today's medical breakthroughs. We are no longer just observers of nature. Thanks to the modern synthesis, we are its editors. From gene therapy to CRISPR, every modern miracle in genomics is a realization of the laws first calculated in a monastery garden. Mendel's final years were defined by a quiet, unwavering confidence. While the world saw a busy abbot consumed by administrative duties, Mendel knew he had unlocked the foundational code of life. He famously predicted, "My time will come," and this slide celebrates that eventual triumph. His legacy is the ultimate outcome of intellectual persistence. He transformed biology from a series of observations into a predictive, mathematical certainty. Today, we don't just remember a monk, we celebrate the architect of modern genetics. Mendel's work proved that truth is patient. By gifting us the blueprints of heredity, he ensured that his time would not just come, it would last forever.